Right. Hopefully this is actually working. Um, I don't know if the audio. Yeah. All right. So, um, I suppose I'm gonna keep the. I'll probably just talk away during this, um, because I know I'm gonna make vods out of this. So even if the streams don't get a lot of people, these people can actually go back and view them. I know Texture Hawk and Alan Wake 2 are kind of close. I know Texture Hawk won by 1 vote, but I'm going to go with Alan Wake instead because I feel like for a stream, it'll be more interesting. Texture Hawk's not the point where I can do some interesting stuff with it. It's a lot of boilerplate, and I don't really think that's going to be very interesting on a stream. Um, so Alan Wake is kind of interesting because I'm actually making some progress with that, and I feel like it would be more educating, I suppose would be the word, to actually see the process. So I have it at the point where I can parse mesh files. So if I'll leave this actually up here. There. There's a few errors because actually I haven't included my new utility library with the new compression codec stuff, but fine, I can fix that. And so the only thing I haven't actually done here myself was, I think I had it open here. Yeah, so the stuff we're reading the talk files is actually from here, so I'll link this in the description, hopefully. I actually remember to do that, but if I don't, at least you can see here this guy has made this code available for doing the talk files because I just really did not want to deal with parsing those talk files or actually trying to figure that out. I like to get into the mesh and animation data. The stuff like the talk files are just um just anything package related unless it's really simple like Ori engine. I hate dealing with because really all you're trying to do is just figure out how to get the fucking data out there. Or so it can be really annoying when I want to get the mesh to kind of figure out the mesh data. So I'll start off with trying to get this working to the point where we can actually start dumping the data again. So let's quickly add my library there. I'll pop into C code. That's fine. Actually build my project information. I hate when this shit does this. Like, so annoying. That was the Microsoft, so it's pretty obvious. Oh, don't tell me I need to include all of my stuff. Like, oh god, I hate this load projects. Do I need don't that? I don't need test. Don't need the standard either. This only has LZ4. Um, this should automatically. Yeah, it does. Okay, I should be able to build that now. All right, so I can now include you. So codec. So I'd like to start dumping some stuff and we can have a look at it and then compare that to the disassembly to see how we can parse this. I do have a parse or per se up here, but there is a lot of data with the skeletal files that I haven't figured out, so we might look at that right now. So if I actually do I even have something in FBX? I don't really want to waste time with. Only dump this. So it doesn't completely blow up. Arrogant. Yes. So have a look at these. So of course I've already figured out the location of where the game loads the mesh data here. So I just open in IDA. It would take too long for me. I don't think it take too long actually. It was just that it's kind of hit and miss. It's just a look at the draw type thing. We're trying to figure out this where this is. To give you an idea of how I found this, because I suppose it would be interesting if you're like stuck, because this game doesn't really have any headers per se. Like, really, this was the only thing differentiating that I kind of knew straight away. Okay, this is doing something here that I'm aware of, because that's a kind of a version per se. Yeah, I think it is, because it's checking like is less than or is greater than. So that would be the only thing that would tell me this is the mesh loading function. That'd be quite hard to lock onto that value, because sometimes what you can do is if the game's loading a pack file or a mesh file, there can sometimes be a header in there, and you can search for that header and see, okay, well, comparing this, like in RE Engine's case, when it came to figuring out like the encryption in RE4, it was just a case of searching for the pack file header magic number, and that got me there. But in this case, a lot of stuff they don't actually bother checking. Like I was actually surprised they checked this value, because even with the TOC files, I couldn't lock onto a magic number to find where they actually loaded from. So, but really what I came down to was I was in a particular location in the game, and I knew I had a fair idea of the name, what the model names would be, and so it was quite easy to, let's say, find, I don't know, a body of a character and then search for that in memory. It was there, and then what you do is you can set a breakpoint in a debugger like x64 debug that will pause the process the minute it hits that memory location, or like a register, something, an instruction tries to read from there. So in that case, I was actually able to see, I think further up the call stack here. If I go jump to xref, it might be in here. I was able to see somewhere in here that excuse me, that it was loading mesh data. So straight away, like, this looks interesting. So I was able to just traverse some of these functions. Like, you look at this one, this one doesn't look very interesting at all. I mean, this just looks like it's initializing a data structure of some kind, because it looks like it's just setting a bunch of stuff to 0, assigning some constants, some stuff here. Doesn't look like it's actually parsing any data. It just looks purely like a that again straight away. So this game has a lot of runtime type information in it. So if I actually run Class Informer, which has thankfully been updated for IDA 9, use the previous. We can use the previously stored result. You can see there's a lot of type information. So that then I was able to deduce from that. If I pop back to this guy and I go jump to xref, I go further up, or I go back, actually back, come from here, go back up the call stack again, and this brought me to this guy. So I can see that a lot of the stuff in the game, excuse me, has kind of like a virtual table per se of loading functions, and I can kind of see that so if we go by this one, it says 240. I haven't relabeled these because I blindly just threw the new exe file into IDA because I hadn't labeled even the original exe that much, so I didn't really care. So this has no labels or any renamed functions like I had in my previous one, but I can kind of see that the 0, 1, 2, the third element is probably going to be the actual function within this that handles loading the data. So you can see that these are standard library stuff, which is sometimes a nightmare to look at in terms of if you see these templates. So if we pop back in here, we can start to deduce some stuff. So let's go back to this function, actually manage the mesh data. That's where I was able to click in here, and eventually I found this. And from this, I was actually able to see, okay, that actually looks like, let's actually open up in FBX. Use HD. Find something a bit basic. I don't want to be too complex. I mean, paper birch stump is only a cup. Let's go with the tire. Tire. If we're able to do something with that, at least we can. So, we can see from this that the mesh file starts off with that constant, very likely a version number. I've already deduced that this has to do with bones. Now, something I haven't figured out yet, and again, this is where I'll have to research this a bit more. The game also has bin skeleton files. And if I try and throw, so if let's find one that actually has bones. Maybe that's just a corpse. So fine. Sort by size. Actually, it'll probably bring us Alex Casey suit. Maybe. Yeah. Okay. Here we go. So you can see this has bones. So the game starts off with, so there's what, 542 bones in here. A lot of bones in these models. A lot of bones. So I did think at first, okay, this actually looks like the parent index. But when I try to use that, so basically I believe it is either a matrix transform or it is an inverse matrix transform. I forget exactly what it is. I think I can look at the code I had here. I think I had like matrix. Okay, no, it is actually just a matrix transform. Or is this actually from the skeleton? I know it's missing. Oh, it is, yeah. So it is. At first I thought this was the parent, but I think when I tried this, it was really messed up. So it didn't make sense at all. So I kind of figured, okay, that's maybe not the mesh data, or not the bone index. And then it got me thinking that maybe the table that's in this is not really a joint table, or well, obviously it is a joint table, but maybe this is just a rest transform, and then it uses the bin skeleton file, and there's another file that dictates how they join up, and this is just purely for skinning data to say, okay, which bones in here correspond with the skeleton file based off of, because if we actually go to the mesh data, you're probably going to see like these all look like this to me looks like a table of skinning data. So there would be, you know, possibly shorts because they have over 255 bones or 256. And then maybe just a single byte to determine the actual influence, because the influences don't need to be super high accurate, so they can just maybe make them bytes. But then it could also just be that these are bytes, because what RE Engine did, and they could do something similar here, because I'm just seeing a, like if these were 16 or shorts, we would see actually 8 times 8 times 2, because it'd be 16 2 bytes per index. And I'm pretty sure when I was looking at the shader code, they do actually have 8 bones per vertex, which is pretty standard. If we pop back up to this guy, so I don't know, did this do anything? So if we pop back into IDA, I think again I deduced that this was, this is where I started to kind of figure out stuff. So you have another V table here for virtual functions, and I think number 9 in this, hold on, actually, and what I can do is can. Am I just blind? Or is it because I've selected that one? Just insert local type. Add type. So I can just do here struct file view table. I think for now. Let's leave that empty for now. Convert to what we can do, yeah, add these in here and then rename them as we see fit. So I'll come back to that in a second because I want to actually determine which are which. So you can see that 72 is have to resend it. So 72 would be 9. That's reading 4 bytes in. So 72 would be like something maybe along the lines of read int in their own source code. So we can see, where's it getting this one from? I guess that's just reading maybe arbitrary data. So this starts off by reading 4 bytes, and then it reads another 4 bytes and assigns it to this. So I can just rename that and say header plus header 8 for 8 bytes in, or no, actually sorry, 4 bytes in. Apologies. We can do, wait for that one and go header 12. Bad declaration myself. Header 12. Just type something. Rename that to header 6. That's header. Again, making the same mistake. This one needs to be header 8. And then this one needs to be header. This starts off by checking the value at header 12. So I think what happens is this value seems to determine how many bone tables are in the file. Because what I'm seeing it do here is start off by saying, alright, let's name that to header. Let's name it to bone table count because it's after reassigning it. So what it seems to do here is read 4 bytes times the bone table count, which seems to read, so if there was maybe, we can see in this case it would read this value, and if there was another bone table it would read another one. But of course there is only one bone table, and I've never seen this value go above 1. If you look at this one, this is the FBI, or I thought the FBIB had bone. Maybe not. But I've never seen it. I've never seen a file have more than one bone table. Maybe they use it for maybe it's a planned feature because I know they have a, you know, maybe for the higher or the lower quality level of details, they might use a different bone table because of course if a character is 500 kilometers away, there is no point in having to traverse 500 bones. You can always just limit that down to maybe 3 bones or something, I don't know. But they never seem to actually use it, even on the higher quality meshes. But that's just because that's just the files I've seen. I haven't actually checked a lot. But they probably do use it because I know they had some presentations they done on the rendering of Alan Wake, and some of them mentioned about how they develop skinning systems from vegetation. It's very possible if we look at a tree or something, it might have it, but I don't know where I'd find a tree. If we search for oak in FBX, maybe? No? We just search for tree. Oh, crap, I forgot. If you're curious about the tool I'm using too, this is everything. This tool is absolutely amazing. It's scans your file system, stores it in a database so that you can quickly search everything. It's amazing how this kind of software needs to be developed for Windows, because they can, instead of Microsoft just making a decent fucking search system. Alright, so can I find something like a plant? Ivy? Maybe? No. Alright, we can come back to that anyway. But it does look like they're storing multiple bone tables, so they start off by reading the bone table counts into this buffer, which is R15 plus 408. So this must be, if I rename this guy to maybe the mesh structure, maybe? It seems to be. Did it not let me rename it? But that's the Elbar type. What I want to do is cannot rename register. Okay, fair enough. Won't let me rename a register variable. So I'm guessing this guy is just a mesh structure, so they load everything into this, so all the data from the file will be this is their serialization method, so they'll load it into a generic data structure in the game. Because I did see stuff in the metadata for the mesh data that lets them decide what to load based off versions, so it wouldn't surprise me if, let's say, you could take files from Control and put them into Alan Wake 2, and the game would just happily accept them. I haven't tested it, but it looks like it could potentially be something that the game supports, because there's a lot of stuff in here that checks the version of the data it's processing and then decides what to load or what to just set to 0. So seems like their engine is quite dynamic in that sense that they can, update stuff, and the game will happily just go, okay, well, this is a newer version I've seen before, so I'll just load the data, but then this is an older version, so I'll just skip that data, or I won't, I'll just set that to 0. So coming back to this guy, where's my, get that out of the way, add, here I can use this, bless it up, where is that, there we go. Where are you? So we can say that we start off with our full byte header. Use handwriting on this thing. So we have what is probably a version. That's 4 bytes. And we have, not sure what that next one is. We'll look into that. That's we're at 0, 4, 8. Again, not sure yet. 4 bytes. And then at 12 we have probably bone table count. That's 4 bytes. And then from that we will read 4 times bone table count. And that will get us each the number of bones in each table. That's why I kind of figured that the table we're seeing in the BinFBX is not exactly the skeleton. It would probably use that and then at some point during runtime link up with the bin skeleton. Which is relatively weird. It'd probably be more sense to just store the skeleton in the, or just, have the table there available to access, or index the skeleton directly, rather than trying to match up at runtime. I mean, it probably doesn't cost them a whole lot in performance. The game runs perfectly fine. But if that's what they're doing, it could make sense, as it would allow them then to just reduce the bone table count in each LOD for, depending on, if they're doing a LOD 4 or lower quality LOD. So We have that much deduced. Back here. So what I wanted to do, I actually bloody forget how to do function declarations in C. I don't often do it. I usually use std function in C++. Not a function, like a function type declaration. That's what I'm looking for. Search that up and see. Like a JavaScript. I don't want JavaScript. Alright, there we go. So if we come back to this guy, we know there's at least, we go A1 maybe. We know there's at least 2, so we can always return the in64T. It's probably or size T, the safe thing, because I mean IDA will automatically in the decompiler try and determine anyway what's happening. So but the more we can do to assist it with its job, the cleaner the decompilation is. So we can do A1, A2. We'll just do a bunch of these. What I'll do actually is I'll do these in VS Code because it'll be easier to, because IDA's whole text editor here is quite primitive. Let's make a bunch of these. A1, A3, A4, A5, A6, A7. And I would just make an array with 10 elements, but I want to be able to rename these individually as I see them. So if we do A10, I don't know how big the vtable actually is. So we'll just leave it at that. If we try and decompile right now, it should. Did I actually save? Hold on, why is it still 1? What a pile of shit. Why isn't it saving? Why it's not saving? Let's try that again, but do stroke. What if I create a new area type? Oh wait, why is it creating a new entry for the hell? Yeah, my knowledge of C type def declarations for functions is completely off. Oh wait, I'm actually dumb. We're making. No, I get it now. I'm doing a type def, which means it's going to create a new type def every time. So it's probably have to generate a bunch of these, and that's why it's not actually entering it. Damn, that's my brain that's not working. Hold on. Oh, okay. Never mind, it's alright. I thought for a minute my mic was low. If it was, you can turn it up, no problem. I am so dumb. This is my knowledge of pure C. I forgot I'm making a type def here, which means this isn't actually an entry in the struct. So I now have to actually, hold on. If I go add type, and I add that as file vtable func. Okay. And then I come over to the, where's my file table gone? Or vtable. So if I open this guy, now I should be able to just do file vtable func. Make a bunch of these. I don't know. I think 10 is enough. I think I've always seen 10 functions in that vtable. I should be able to do that. Yeah, there we go. Alright, so now that's 50. So now if we decompile this, yeah, so now ida is going to introduce that variable for us because it's coming off the struct. So I should be able to now come up here and say that A10, if I rename A10 to maybe read, let's just call it uint32. So now we can know if we see that, we know we're reading a 32 bit. Are you? Don't like you. Jump to xref, where are you? Or is 27 is the actual, what's v184? Memory file vtable? Does that inherit from base file? Hold on. If it is, I can just set it to the same value. File stream. No, they're not the same. Oh, well, that's okay. So, what's happening here? Like it says, we're reading the bone. So we got the bone table count. That will bring us. So if we take, probably should try a smaller file with less bones. Have a look at because have a look at something here. There's something here that's small, has bones. Too many bones, just absolutely. I'll just make a script actually. I think the characters are going to be our best bet because bones. 197 cheese. NPC. Huh. This looks different than the other bin FBXs I've looked at. So is this? This is completely different. It's like a static connector. I mean, I know we have the. Oh, not even the same. Okay, we need. These ones are completely different, actually. Huh. I mean, it looks like it has mesh data in here, but or you know what it could be. I mean, I'm gonna blame my tool on that. It looks like it has the data in there, but it just hasn't exported correctly, or it's pulled incorrect data. So yeah, I think we're gonna be stuck with using one of these characters for now. So I think probably the easiest thing to help understand the layout of this file, also something that can be easy to follow along to, is maybe a Python script. I think would probably be the best thing. Let's get it's just a blank, yeah. So let's go open folder. Let's see code janitor. Can I create a folder in here, please? Am I pressing right? Oh, there we go. This thing. Let's just call this folder. So call this bin fbx parser. Boy. Import struct. And let's focus on that one. We were looking at the potato D6. Yeah, let's focus on this guy as test to, because I haven't actually done the bone data, because once you get actually it's gonna be quite a long time before we get down to that. You kind of start looking at this data here, which I haven't actually looked at yet. So it'll be interesting to see when we get. My goal with this is to eventually hit the mesh data, which is further down. So if we go first off, get the file name. To file path equals that. And I can't be bothered to escape all of them, so we'll just do that. So we have 4 bytes. I already know how to parse that initial bone table, so we know that for, well, how do we put this, for, let's just say bone count, we will parse the string size, which is 4 bytes. The actual string, which is this guy here. We have a 64, I believe, byte matrix. So what does that include? A 14. Oh yes, this does include the null terminating character. Then we should end up with 64. Is this where it didn't make sense to me? So this one is actually pointing already to bone 9 as the parent bone. That's why I don't think this is the bone parent index, but I believe when I did parse the bin skeleton, it made more sense. It looked a bit more like an actual skeleton. So that's why I'm thinking that this table is just a rest transform. Because all of these are in world space, because I have just dumped these without any, just as is, no bone parents, no nothing, just dump. And these are world transforms, so I'm guessing this is something else maybe, I don't know. Maybe it's an index 4, the bin skeleton, like maybe a helper value of some kind that tells it, okay, it's this one matches up with index 9 in the source table. But again, then that wouldn't really make sense, because now you're kind of saying like, what's the point in doing all this? So let's continue anyway. We go 64. Just try and keep these sane. If we go matrix, 64 characters, and then there is this unknown, which is 4. So if we keep that in mind, we can do, open path in text mode, RB binary F pass for now. So I guess we'll actually immediately start going header buffer. Pack. I'm gonna read f dot read 16 bytes from the header. We know the header is 16 bytes. Every bone or every mesh file in this game will have 16 bytes to start off with, and then everything else is up to whatever is in the header. So we know this is a bone table count of some kind. It does dictate how many, I suppose, bone tables there are, or how much of these there are, which are counts for the bone table. But they could be, maybe skinning kind of. We know that at the very least this one correlates to how many of these. Now it's all, like I said, it's always been 1, and even if there isn't a bone table present, it'll still be 1, and then the value will be 0 here. So even if this has never been anything but 1 in all the examples I've seen, but it is a value that can change, and that's why sometimes it is worth looking at IDA, because you can look at a file like this, and you can look at a bunch of samples like that and see, okay, well, this is probably a constant because it never changes. But if you actually look at IDA, you can see it actually has the potential to change. And what you end up with in a situation like that is you're parsing a bunch of these bin FBXs that you're testing, and you're like, oh, everything's working for me. And then a user comes and says, oh, it's not working for this one file. And that's when you find out. So if you can get away with a lot with just sampling the files like this, where we just look at them in a hex editor and see what's changing, and kind of deduce the structure from just looking at this file. Like, there is a lot we can just do. Like, I didn't even bother trying to see this, because I know it's pretty easy to see. We have a string count, or a character count for the string. We have 64 bytes, and then we have 4 bytes, and that's constant. That's easy to deduce. What gets a bit more complex, which I did need IDA for, to properly parse, which is probably way down here. Yeah, we'll look at it in a minute. So I ain't going to bother trying to find it, because I have to click through a bunch of functions to see where it is the mesh data. That is variable length. It is quite, I wouldn't say complicated, because really all it is just different values. But what a lot of games will try and do is keep the structures in the files constant. or at the very least, if we're parsing, let's say, the mesh metadata, it will be constant and then maybe point to other data that tells it what to do. Oh, what I found with Alan Wake is there's a bunch of inner loops doing stuff. Whereas I find with a lot of other games, they'll try and just like parse a data structure all in one go and try and even fit that data structure to the in-game data structures. So what you end up with is a way for them to just quickly load everything all at once without having to do a bunch of file calls. Because what they're ending up doing here, I don't know. Again, you want to profile this. They probably, I'm sure this works for them because the game looks and runs amazing, at least on my PC. I know it is a heavy game to run though in general, but what you end up with is a bunch of calls to these virtual, especially a lot of these virtual functions. They're calling a lot. Like they could be calling, so they'll traverse all the meshes, and then they'll call obviously this value. They'll read a bunch of bytes from the buffer, but then they're going to be doing that again in another loop within the mesh loop to load, let's say, the mesh primitives. Instead of just say, like, some developers would look at an approach and say, okay, well, we never go above, let's say, 8 mesh primitives. And when I say primitives, I mean stuff like, or not primitives, attributes. When I say attributes, I mean like normals, tangents, skinning data, positions. And they might just make that table a constant size. Alan Wake does have an advantage though, because you end up with a situation like Black Ops 3, where when we try and do anything that goes above the limits of the game, it just throws a big tantrum because everything is so heavily pre-allocated. Whereas in Alan Wake's case, it'll give them a lot of flexibility to say, well, now we want to render a world that's like 4 gigabytes. And we can do that because, or let's say it has a bunch of attributes in a mesh, and we can do that because our engine isn't constrained to these fixed limitations we put in place. So, I mean, Call of Duty's argument for that is that their game has been just slowly developed from the years. So, I know Alan Wake, they've completely redone this engine from the ground up for Alan Wake 2, or not even Alan Wake 2, it was a Control or those older games. I know this is very similar from what I've seen in Control and Quantum, but this is completely different to them. A lot of research I'm doing here can't be applied to them. You probably need to just start from scratch from what I've seen in their mesh files. But there is some stuff that's similar, so there's that. Let's get parsing this bone table and see where we end up. So if we parse that, I'm going to skip that header value and just go straight to the bone count, because I know for now at least it's constant. And we'll go read 4 and cut that out. Then we can do 4. And we can do, so we're going to start off with reading the string size and do struct read 4, grab you out, and then the actual string val is just f.read because we just want to read the string size. And I'm gonna skip the data here for now because I don't really care about it. So 68 bytes constant. We're not gonna bother parsing out right now. And if we even just print string val dot decode, and I know it's UTF-8 header array, well, it's probably just ASCII, but UTF. We hit that, hit run. We hit the Python file. And we now have a shit ton of joints. A lot. So, like I said, this game has a lot of bones in the characters, especially. Doesn't look like they're doing blend shapes because I couldn't see any data. So, I haven't looked at it that much yet, but at least in what I did look at, it doesn't look like there's blend shapes. It seems like it is all done through these. Like, you know, you have like cheekbones and brow bone and, you know, eye bones. So again, I've never done game development in terms of rendering enough to know how much. Yeah, I mean this one has. Hold on, pop back up here. This one has 596. I've seen one with 800. So I'd always love to know from both memory and performance, like what's the advantage? Because I know at the very least you are paying. Well, it depends on how they do them. I know Call of Duty has recently started to do all skinning and stuff like that on compute shaders, which I think explains why Modern Warfare didn't really use blend shapes as much, because all of their skinning is done on the GPU through a compute shader. So it probably doesn't cost them a whole lot to do it through skeletal bones. But I suppose I'm not a game dev in that sense to know. I think once you're getting to that point of developing an engine the size of, let's say, Call of Duty or this one, it's a completely different ball game when it comes to profiles. So we're at 55k. So we pop there. So we end up here. So I pop back into IDA. Roll back up here to this guy. So that reads that. Does this do anything? We're not even passing the file. Yeah, let me rename that to FP. Where do we get that again? Is V128 just another reassigned variable? Oh. Alright. Like it's mixing and matching calling from this file stream vtable and the other one from here. Why? But we pop back down here. Yeah, like it's mixing. I wonder if this is the same vtable. So if I go convert to struct, pop that guy in there. Is this? No, that won't work. Alright, so yeah, it is completely different. So we're coming down. So we read this is the header, gotten these values, and then this guy here. Maybe this is so I think with this one, I think the reason they're mixing and matching is because this one might just copy. Yeah, because if we rename that to bone string size. Yeah, that makes sense because they're going to mix and match them, because they might just use this one for the ease of access to, let's say, read uint32. And then they're going to swap back over here because they can just call the other one for just, I just want to copy characters from this array. And this is probably the bone array. So is that constant or no? So there's actually a pointer. Do they allocate anywhere? Where do they allocate this? B40. Alright, so they might pre-allocate this array maybe somewhere else. Yeah. So I'm guessing they just have like the bone buffer allocated somewhere else. And that's how they're just reading into that and then incrementing it each time. So we have FP. Alright, so where does it complete finishing the bone read? Or maybe it's in here. This guy here. Oh, Jesus Christ, there's a lot of bloody SIMD intrinsics, or well, instructions, because I don't want to decompile them. And I can't use the microwave VX plugin on this. This is the leaked IDA 9 build. I'm guessing maybe. Let's see, because this looks like we're reading that 4 bytes that we saw here, which is the number of characters in the string, and then it just copies that. But then I want to see where. No, it could just be the IDAs. Oh, yeah, here it is. Okay, this might be it. Yeah. Yeah. Okay. So it's reading here. So this is some probably other function, that a helper function of some kind to read bytes again from the list. Suppose there the buffer straight in. So there's 68 bytes here. That completes the bone read. And we just do that for each bone table. So I suppose I can call this maybe memory file underscore read buffer. That's fine. Yeah, because this looks like what it's doing here is it's just accessing the raw buffer. But then I don't know, maybe this function does some processing because this is a string, whereas this is just literally them asking for we want 68 bytes, whereas this is actually copying characters. So I'm guessing maybe that's doing something different. We can actually look at that if I reset this back to reset pointer type, because I probably kind of, yeah. Like you can, like I say, I don't know if you're here when I was saying it, you can just juice a lot by looking at this, but the problem is you have situations like when I was looking at these files, I noticed that this value never changes. So logically, you might just say, okay, that's just a constant. But if you actually look at the game's code, because this never changes, even if a file has no bones, this is always 1 and this is always 0. But what this is actually saying is how many bone tables do we have? Because if we look at the game code here, what they're doing is they're taking header 12 bytes in, and they're going to read 4 bytes per each iteration of this, and then they're going to go here, they're going to go for each bone table and loop that number up here, which means we could potentially have multiple bone tables, which logically, if you could look at that approach and say, okay, all the files I looked at are 1, so I'm going to assume that value is useless. But then someone tries the tool and they run into a situation where you have a file, you have like 100 different files that have this value that's actually different, and you end up with your tool crashing, and now you're trying to figure out. So that's why I think there's advantages to just looking at the files as is. Alan Wake is a bit different, where I do think this approach is needed, the whole looking at it in IDA. You have games like Ori Engine and Call of Duty, which what's very common is for them to just say, I have an array of mesh data, read 128 bytes per each one. Alan Wake, a lot of it's variable linked. I think it's for Alan Wake does it purely for flexibility. I think their engine is really flexible, in the sense that they can have different amounts of data of variable length. No, in fact, they even have type information in here. So when I was first trying to figure out, this is the mesh loader function. When I was first trying to figure this out, I had to I actually had to debug the game, find the mesh in memory, put a breakpoint on that, then it hit this, and then I knew straight away from this value, because this is the version number that we're now dealing with the mesh data. None of it's obfuscated. There's no well, if there's DRM, it doesn't get in my way. The exe file can be opened up as is, and you have all this type information here. Like if I I can now find any of them by just searching for request load, because they have the runtime type information here. So you have stuff like the skeleton data, now to be fair, all these do is serialize the data or deserialize the data, so it just loads it into the internal game structures, which is still quite useful because at least it gives us a high level overview of the file. So it was how I was able to, if I come back into the janitor project I have here. So for example, this is the mesh metadata function. So again, one of the things I had to figure out by debugging the game was if do I have a dump of the, where is it? I wonder does my tool actually dump it? I do, temp.dat, right. This is the actual package file. Now, as I said at the start of the stream, big shout out to this guy, or this project at least, on GitHub. So because this just saved me so much time trying to figure out the actual package data. This is a tool that will just unpack the packages, and it's fucking 100. Really glad he made it open source, because it's just helped me, because at least then I can actually focus on the mesh data. But one of the things I noticed, and I was trying to look through the code to see, do they do it? So there's this because I was always trying to figure out how did they actually figure out, because even in the smallest files I was looking at, I was always wondering how did they know, or probably easier actually if I show an example. So you can see they have data here, and if we pop down here, you see there's the index data, but then all of a sudden we have vertex data again. So one of the things I had to figure out was how do we know where this is? because there's no matter how hard I looked up here, there was no data up here to tell it how big all this data is. So I figured, okay, well, they must calculate it in the mesh function. But then I figured out if you come back here, this is the initial like mesh loader. Before we even got here, they had all the offsets for the data, and this is where IDA is really useful for actually figuring and debugging the game. I was able to see here in this little structure here, we already had all the sizes of the mesh data. I was like, how the fuck did they do that? Now if we come back to the package file again, we can scroll all the way down here. And we have this, which is so it's reversed because of LiTTiEngine. This is the pack file metadata. So within this package file, they have more metadata that's separate from the actual mesh, the actual files. And I think this gives the game a way before they even start unpacking. So if the game requests a mesh file, I imagine they can possibly use this metadata to start telling it, okay, I'm going to have that thread over there start unpacking the data, but while that thread is unpacking the data, I want the GPU thread to start allocating the memory I need, so that when that thread is done, we can just copy all the data over. So I imagine there's way, like, the engine is quite good, and that's they have a lot of stuff in here it might seem stupid on the outside, but you have to understand the stuff they're trying to target. They do. There is some stuff where I just don't understand what they're doing. Like, you take a game like RE Engine. RE Engine is both simple and complex. It's complex where it needs to be complex, and it's simple where it needs to be simple. Like the pack file for, I don't know if we take a pack. All right, there we go. Yeah, there's one straight away. Now I can't use RE4s because that one's encrypted, but I can use this one. So here's RE8. You can see how dead simple this is. We just have a list of all the data, or the entries within this package file, and then here's all the data, and then we just have offsets to it, and that's it. And then you just parse those files as you process them. And you have games like this where it's just like you have this elaborate system of tables upon tables of data. You have folder structures, file. Then you have a table of how many buffers are in each one. It's some of it makes sense again, and you have, I suppose, they have their reasons for doing it. Yeah, that's what I never understood, because so again, looking at the tire, so this one's fairly structured because it's not changing, but so this one's 115, I think, something bytes. The problem is that they have arbitrary linked mesh there. So I think it starts off somewhere around here. You know, the first mesh you parse might be 86 bytes, then the next one, that's why you have to like understand all the different data that's in here. So like even here, I think this looks like where the attributes are. No, that's the thing. It doesn't need to be that complex. Like again, you take an engine like RE Engine, runs really well, and looks kind of the same as some of these games, and is not as complicated. I think Capcom made the best choice ever with regards to RE Engine. Just don't make it overly complicated. Even Call of Duty is not this complicated, which is funny. So getting back to this, so we're at 68 bytes here, so we're going to assume we're done here. We're going to come down here. So then we're starting with header 8, the 8 byte in. And for this particular one, we have 1. So we do have whatever this dictates. It runs fine on my PC, but I will say it doesn't run. Like I always said, you look at, so if we take Cold War compared to Modern Warfare, like Treyarch have this really weird, elaborate G buffer rendering system, and I'm sure you know the whole mixed tile system, mixed map system, and all that, trying to optimize texture usage. The game still runs like ass and looks worse than Modern Warfare. And Modern Warfare just uses normal textures with a forward renderer. So I don't. Sometimes I always wonder, like when these devs do these elaborate like rendering systems and that, like, where's the trade off? Because it still runs like ass. Like Cold War ran like ass. Um, and Modern Warfare ran like butter, at least on my PC. And that was back when I had an RX 480 and the game ran at 100 plus FPS. Whereas Cold War could drop to 80 or even 60 at times in zombies. So yeah, I always wonder when they do these things, what's the actual purpose? Because I don't see the benefits in the real world performance. So I don't know, maybe they just, like you say, maybe they just like the flex. So we start off with this. So we have header 8. Doesn't look like we're doing any file processing in this function because we're not passing in any of the file pointers. And so we start off here FPA9. They started to do that in Vanguard. In Vanguard's case, they would actually store like, so they might use one material, and then it might have like multiple color maps. It really make a whole lot of sense. Just have multiple materials. Yeah, I mean, it definitely reduces a draw call maybe. Doesn't really reduce much in the sense of, I mean, with DX12, you see, I have no experience with DX12. I have a bit with most of my experience with DX11 is with dealing with compute shaders, so I don't deal a lot with the low level stuff of trying to make things run as good as possible. I just want to send stuff to the GPU, get it to do stuff, get it back. But my understanding with DX12 is you just build a command list and you just send it off to the GPU. So I thought the whole thing is that you could, in theory, just send a million materials off to your GPU, and it won't care because it's the same as rendering, you know, so many. Like if they're, and what I mean is, so you're sending off a million materials with, let's say, a million individual textures versus one material with a million. Like you're still having to allocate those textures anyway and assign them and, you know, sort them. So I have found that I found a lot of games. I found when RE Engine first introduced DX12, it stuttered a lot on my RX 480. And when I switched back to DX11, it ran fine. Of course, on my newer 7900 XT, DX12 runs fine, but I have found, especially on older GPUs, that DX12 is actually a hurts performance. And then of course there's probably the driver optimization for some of that, which has improved a bit. What are we doing here? A9. So what's A9? A2, A3, A4. So A 3, 4, 5, 6, 7, 8. What's this doing? This is reading 4 bytes. Yeah, I guess so. 48. So what we're doing here is A9 seems to be reading an integer, and I can tell that, yeah, because look, it's kind of deduced unsigned int. So if we rename this to maybe rename field int, and not read int. We already have read int 32, but if we just do 2, we can try and figure out what's the difference. I mean, one could, I know a couple of them look like they're reading 4 bytes, and you know, you might look at it and say, okay, that's an int, but it's actually reading a floating point number. That's why they would have multiple. And what they could possibly do as well is, even though you might see like that this has multiple versions of a function that reads 4 bytes, it probably gets generated because they will do a template and then they'll just tell that, and then of course the compiler will generate multiple functions. So that's probably why there's multiple things that look like they're just reading a uint, but they're actually reading something different. Like this value could very well be, let's say, a type, and they just generated a new function for it. But IDA, because IDA doesn't have any type information to go off of, it just goes, okay, well, this is an integer. Because the decompiler will just try and see, okay, well, what are you trying to do? And it'll go by register names, like, actually, that is RDI, so it's a 64-bit. But if it was to see, like, EAX, it'll probably go, yeah, that's it's what you call it. That's an integer, and of course it will also try and look at, let's say, I don't know if this function loads. So if I just use an instruction, probably loading memory and then doing this, it'll probably say, okay, well, that's a pointer. So this is loading something that's aligned. Right, so let's have a look at this. We come back here, go to this. We start off by reading that. So that's a count, very likely. And then that's possibly a hash. Maybe. It's a fairly big number and it doesn't look like, but then it could just be a very, very, very small floating point number. But if we, I mean, yeah, this looks like where we need to be. This all looks correct. So the game starts off by reading this, and if we rename this to count 0, no, just give it a name so I'm not just looking at V12 and V20. So this is just, yeah, we can ignore these functions because you can kind of tell, because really what I'm interested in here is to try and figure out the general high level layout of this file. And I know we can ignore these because this is the file pointer. The file pointer, like even if we take this one for example, the file pointer is not being passed into this function, which means I can say with certainty that this function is not going to read data. It's just going to do something with these counts. So I don't really care about that for now because I'm more interested in what's reading data to get a general idea of the function of the file layout. So again, this is probably just because I can see like that they're switching between these two. So they probably have, my guess is they probably have file pointer. So they probably have like a file stream table, and that wraps around a file, a base file, because like memory file inherits from base file in this game, and I'm guessing file stream is just a wrapper around that. And then so in the same way in C#, you can create a binary stream from a memory stream, or a binary reader from a memory stream. You can still access that memory stream because there are some advantages to reading directly from the memory stream because there are some optimizations there for copying for buffers. So they're probably doing the same thing here, where when they want to, they'll skip accessing the file stream and just go, or the file stream, and go straight for the memory file instance. That would explain why they're switching between these two constantly, because when they just want to read bytes from this, they'll just quickly go, okay, I'm going to go straight to the memory file because I know what I'm doing. Instead of, because this might have overheads for reading from buffers of like creating stuff and allocating memory. So this is going to read 48 bytes. So we start by reading 2. So straight away we can go, let's come down here. We can go, well, now we just call it uncount and hash val. Let's call it hash val for now, and struct unpack read points. Pretty sure that works actually. Let me see. I think that works if I just do the two variables like that. It'll automatically unpack the tuple. Kula bula. I'm not too up to date with some of these modern features in Python. I know there's now some form of type declarations where you can do, oh, what was it? It was like if you have a function like def method, you can now do, I think is it, let's say value and then str. Yeah, I think that's it. And then let you pass. Yeah, you can now do that, and it's just, I guess it makes sense, but it's like, at least it's not forced on you. Because there are times when I'm just throwing down scripts like this, I don't want to start typing out type defs. But I suppose if you're looking at, because you see the way they do it here, like they can do format string or bytes, and then this is like a readable buffer to just let you know. Yeah, that's the thing. I haven't used Python. I have rarely been using Python, but I figured for this it might be a good way because at least you can follow along. I suppose a lot of people know Python. A lot of people might not know C#. So it might be harder for people to follow along with me trying to deduce this file structure and unpack it in some form of code. But yeah, there's a lot of new features in Python I haven't been up to date on. That one's cool. I mean, it's nice that you're able to do type def declarations, but it's also nice that they don't force it on you, because you have situations like this where I come back to the language after a long time and I can still just happily throw down code without having to think about it. So we got uncount. Oh my god, we got Stig. That is insane. Yeah, that's the way I usually handle it. I use Python for stuff like this where it's just a proof of concept. I'm not really trying to make something usable here. So it's really nice for stuff like this where I just want to throw down code. I don't want compilers. I don't want to set up stuff. I'm just able to create a folder in VS Code and just start typing code, and I don't have to worry about errors. So this is going to count plus one. This is going to go +1, but you'll have to notice this is where you need to understand IDIS compiler or decompiler, because you might look at this and say, oh, +1, but sure, what's going on up here? What this is doing is casting, and I don't know why sometimes it does this, but it does. And this is where you need to help IDA by giving it stuff like this, like file. It's going to cast it to a keyword pointer and then add one onto that, but it's not adding one byte. It's adding 8 bytes because we are incrementing the pointer, which is now a keyword pointer, and adding one. And I don't know why it does that sometimes, so I can just do this because I'd rather look at it this way. I can do reset pointer type, and there we go. Now it's going +8 because sometimes I rather look at it from a pure bytes point of view. That's a good trick in IDA. You can just right click and reset pointer type, and what it'll do then is this will just become, you know, like that. And you can also just hint at it by, I don't know, you can also make that a character array. Otherwise, you're going to look at confusing situations like that where I look at this and it says +1, but then this one also says +1, but this one is actually a keyword pointer, and this one's actually an in pointer. So what we're going to do is +16. Where are we getting count +16? 43 +112. What are we doing? Oh, what are we doing here actually? Or is this doing something with the value? It needs to be doing something. So +16. So we're going to copy 48 bytes, but my concern is what's +16. So this is where I'll want to debug the game, because I kind of want to see why. Because what I'm seeing here is they obviously are. This is obviously v45, possibly, let's say the buffer of all of this data, and then they're going to go to the element they want, and then they're going to start unpacking this data into that buffer. But what I'm finding confusing here is that they're reading into count 0, they're reading into the byte 0, and then they're reading into byte 4. But then down here, they're taking 16, and then, yeah, it makes no sense. Unless what they're doing, that's where this function, that's where we might actually want to look at this. Or maybe this one. And see what are they actually doing to +16. So we're in here now. So let's have a look at this. So +8. So this is obviously a pointer to that data, so +8. Yeah. Oh yeah, so they're assigning. Okay, that makes sense. Yeah, it is just that value. But if it was any more complicated, I would just boot up the game and start debugging and see what is actually +16. What's at the 16 byte? Because otherwise you just spend so much time trying to figure this out. So let's have a look and see what happens if we go. You see, this is where it doesn't make sense. Like, why do we have so many? So I'm guessing they have like internal little structures in here, and it's just assigning the same value to each of these, and it's just that's where it doesn't make sense. Like, why are you doing this? I know they're probably smoking. So we should be able to do buffer 0 is equal to f.read 48 times. What was it? Uncount. And we should be able to do print f.tell. See where that ends up. So now we're here. And if we come down to here, yeah, so it actually makes sense. Yeah, because we're ending up with what looks like newer. These are all floating point values, and now we're hitting here, which looks different. So if I pop this guy over here, I'm trying a vertical monitor over here. I'll probably convert that back to landscape because this is so weird. I mean, for some stuff, cool. Like for the I have a Wacom tablet, and for that kind of stuff, like I can pop open this guy here. It does work for this, and I do like that OBS. If I minimize this, it'll automatically hide it, and I can just pop it back up, and I don't have to manually. So we now know we have what is. I know, just call it count. That's 4 bytes, and then what looks like a hash of some kind. It doesn't seem to be used at this point. And then if we come off this guy, we will have 48 times UC, we just call it UC for uncount. And then let's try buffer 1. And what does it do next then? If it's come back here, so unc then is 4 times this. Four times. Again, 4, 4, so 3 4s. Let's do 1, 3. And then here, this is where it's doing something a little different. So let's wait until we hit that data. So we're now at 102. Yeah, so we're now here. This one is actually, they actually perform some alignment here, or unpacking it. So this could actually, they're definitely doing this alignment thing, but this guy here, this whole shifting 6 bytes, that could actually be a compiler optimization. Like if you do, is it modulus? Is that the one? Is that the one where like you get the remainder? Like if you do modulus 2, the compiler might actually do like a shift operation automatically under the hood. Like if you're doing modulus 2, it knows that, like, that's why sometimes you're better off to just not do micro optimizations, because the compiler will likely do it. I don't know if that's what they did here, but it could be, because what they're probably doing here is they say 8 times this, and then they're probably modulus or dividing it by something, and then the compiler's going, yeah, well, I can make that more optimized. Compiler optimization is crazy. I don't know. Those guys are on a different level. They're like waking up every day and they're going, what am I going to do today? I'm going to make a new compiler. Weirdos, but they make the world perfect. So for this particular one, we need to go 8 times. Let's open the actual Python console so I can kind of type this out, because copying it straight from IDA is obviously not going to work. So it's going to be, let's take the value we actually got, for example. There it is. So we're back here. We can go 770. 770 plus 63. And so whenever you see stuff like that being done, that's the 832. Whenever you see stuff like this being done, where they add a number and then use the AND operation, very likely it's for it's alignment. So they're trying to say we want to make sure this value aligns to a certain value. So 770 might not divide by, let's say, 8 or 16. So they might want to align this to so if I go 832 divided by 64, it's very likely they're trying to divide the or align to 63 bytes. Obviously I can straight away tell that 770 would not divide by 64, whereas so 832 will. So that would just simply take that value and align it. Again, that's kind of the whole byte-wise max you can do. Possible a compiler did that. Very likely they did it themselves, because usually it's easier just to do that if you just do plus and then use a AND operation. So if we pick this guy, then we're going to do 832 and shift that 6, which gives us 13 bytes. So we come back to, where was it? Was it this guy? Oh, don't save. And I have to close that and reopen it because the HXD is stupid and will now hold a lock to the file. So we go 8 times 13, 104. That makes sense. It looks like we're supposed to end here. You can kind of see how the data kind of changes. We now have a new value here to work with. So kind of makes sense. Probably it's, so if we do 8 times, we're gonna go pop this guy in here, another one, because we want to shift 6 bytes, and then, but we also want to replace this with unc count. Just pop a compile there. So now we're supposed to end up here, which is where we want to be. So we now have something here that can kind of traverse this file. Obviously we're not done yet, but we're starting to get there in regards to, now I'm going to guess that a lot of whatever the hell this data is, we can probably ignore, but you see, I'm thinking this actually might be, these look like indices. So maybe when I was thinking, because I was wondering, because they all said bin skeleton, I'm thinking that maybe this is the parent table, but then that doesn't make sense. Because, hold on, if we go back here, do the bone counts match up? No, maybe not, because come back to where this starts. We go. That's 770. Yeah, no, that doesn't make sense. But then you see, maybe there is the skeleton file that it references. So I haven't included any of this does, but really I don't need to know for now. If we're just talking pure like traversing the file, that's where we can start to figure that out. Oh, so yeah, so 63, because when you're aligning a value, what you'll do is you'll do the number you have right now plus the number you want to align to. So if you're at 770, so I suppose you can kind of get an idea by, we want to be aligned to 64 bytes. So we're going to add the value we want to align to, but that won't work because the bits won't be corrected. Like, so we'll go to minus what we want to be. So minus 1, so 63. That gives us 833, but that's still not correct. So we'll just use simple byte-wise math then to now get us to where we want to be. So there you go. A bit more, it's obviously way more complex than that, because there's this whole byte manipulation under the hood. But basically what you're doing is you're adding the value you want to align to minus 1. And then you're adding, I think this is the inverse. So if I do 63, if I do 63, does that do the same thing? I see, it won't work with Python because Python's numbers work different under the hood, so I can't really do that. Yeah. Or can I look at what 64 looks like as a HXD is usually good for this. Yeah, so you can see that that's 64 inverted per se. Like the bytes have been, yeah. So basically, then this is just mask that, and then it will, these bits down here obviously won't be masked. That's essentially what that's doing. Like I said, it's a lot more complex than that, but that's a simple overview of how the alignment works. You're just adding the number you want minus 1, and then you're doing the Yeah, so basically you're maybe if I rephrase, you're doing the number you want, add on the number you want -1, and then you're bitewise ending the inverse, the bitewise inverse, I suppose. Is that the name of that operator? Hold on. Bitewise inverse. Yeah, it's called inverse. Yeah, you're doing the inverse, which gives you like the bits. So if you might, now your bits are like reversed. So you're masking using that, and that'll get you the value you want because it kind of trims off those extra bits you don't want, and that brings you down to where you want to be. That's why if you ever want to, you can literally just do it through Python. If you ever just wanted to, you can just literally go. Like I said, you can go. If I want to align to 8 bytes, I can do. Or yeah, and it gives you -9. You can just cool trick, but I mean, most of the time, you can just. I just when I'm doing shit like that these days, I just ask ChatGPT, do this for me. As much as I don't want to go along with AI, it's here to stay, so I'll use it for stuff like that. Yeah, as long as you can vet the results you get from AI, you're fine. All right, let's go back to this. Yeah, for stuff like that, I will happily use ChatGPT. Give me something that aligns the value. Actually, hold on. I think I did say it to you. I actually might show you that example. Hold on. I know I was mentioning to you like where ChatGPT fails, and it's where it gets really complex, or when you try and ask it to do stuff that is completely different. So where is it here? It's in here. It was when I was asking it about emulating ARM code. But is this the function? I know I accidentally had two. Yeah, there's two here. Hold on. So here we go. So you can see when it just kept failing to give me what I wanted. I think here when I was asking it to like, yeah, no matter what I said to it, yeah, it just did not work. It kept trying to lock onto the solution that was not working, and even when I tried to, I would try and get it to go the right way, but what would happen was, what was happening was, it just kept reversing back to its original shitty solution. So we have Blick in the chat, by the way. We have Blick. That's an honor. It kept locking onto the same solution. I had the same problem when I was kind of asking it. Yeah, it tries, but like I said, I remember asking it because when I was trying to figure out Alan Wake's vertex normals, I ended up actually figuring them out from a presentation. And now I know now that I've seen the presentation, they had God, if I can even find it, Alan Wake 2 vegetation. They had a whole GDC thing here on. Let me download this. Probably telling me do I want to no. I'll save it. So this is how I figured out Alan Wake's vertex normals. This is why sometimes the way you figure it out is not true reverse engineering the game. Like the way I figured out what's it called, the normal maps in Infinite Warfare and Modern Warfare 2019, and even the newer games, obviously, because they all use Nog, was through a presentation that Infinity Ward have done in rendering. But this is why sometimes it's not about reverse engineering, it's just about research in just pure like PDFs and whatever the game has done. So if we scroll down here, I think it's in this one. Yeah, here we go. This is how I figured out. So this is where they show literally how they stored vertex data, and it was completely different to what I was looking at. So this is how I knew I wasn't even on the right track. I was looking at it from a Modern Warfare point of view, where they were doing like maybe quaternion encoding, but no, they actually store part of the normal, which is Noctahedron normal, in the position data, and then store the rest here as tree. I actually found out again with more research, this is actually very common because you want one of the elements to be a higher precision. For whatever reason, I didn't look into why, but it's apparently required, or it's required for accurate vertex normals, and then the rest is just stored down here. Yeah, it's just crazy. But I knew now looking at that, because now when I look at that, and then I go back to the shader code, which I probably lost now because I have moved around that stuff. Actually, can I find it? DX12 or DX? Maybe I still have it. If I look at this one, this might be the shader code. I know now. If I look at this, we'll just let's see. Will you see? I think it's down here where it starts to do it. So if I do 1023, that'll probably get me to it. Yeah, so if we look down here, I started to see now that this is very similar to how you would convert a octahedron back to just XYZ. So yeah, I figure I if I probably spent enough time on this, I probably would have eventually deduced that was what they're doing. Because you can start to see stuff here like, you know, subtracting -1, doing stuff like that, and then taking the two numbers and adding them together. But really, times when I'm just watching TV, I might go look at Alan Wake, GDCP presentations and SIGGRAPH stuff, and you end up finding stuff like this in there where they actually talk, because this stuff they're not doing it, you know, they're not packing their normals this way to try and hide it. They're just doing it because it's optimized, so they have no problem telling people how this is done. Yeah, this is always an interesting thing to do if you're ever reverse engineering games. Look at their SIGGRAPHs if you're like stuck on Vertex data. Hello, Echo. Yeah, no, I was just saying like why they do this or how it's done. So you basically take the number -1, then this is the inverse of 63. I don't know what these values are, so we're just trying to read the buffer, trying to get a high level reader going on so that we can just traverse the file. We're not interested at the moment in what the data actually is. That's for later. But what I'm more interested in right now is getting through the file and seeing if we can at least get to the mesh data, because I know how to parse the mesh data. It's this data I haven't looked at yet, so I figured it was an interesting place to start, because when I started at this, I was at 0.0 at the start of the stream, so I'm now able to get to the point where I can traverse all of this guy's data. So we pop open our thing again. So now what I'm going to do is get 4 times. So now we should actually probably be at the end of this data. I pop this guy in here, go to HXD, open this. We're now at this data. So is there more to parse? We now have these. Let's make sure we're actually at the right stuff. We just take this out and make sure. Yeah, it could be, because especially with the GPU, the GPU loves aligned data. So if you're sending stuff, especially since you use DX12, because like it wouldn't surprise me if they take all this data and just send it straight to the GPU. And that's just all they do. So having it aligned to, and yeah, definitely for SIMD. Like you want stuff, I think is like 16 bytes for a lot of SIMD intrinsics. So if it's not aligned, it won't really work. And then there's just pure memory management, just like purely for memory, because I know your CPU likes stuff to be aligned, especially for, you know, reading into registers. Because I think like, for example, if you have stuff spread across multiple bytes, it's like multiple reads. And not only that, you can also have cache misses now, because your data might be spread across multiple cache lines. So what you end up happening is that your CPU now has to make 2 calls to your RAM for memory when you're reading stuff in, because your data now might be spread across 2 cache lines. So you end up with cache misses purely because your data is misaligned. That might be why they do it as well. In this case, with it being aligned to 63 bytes, or 64, sorry, that's such a high number, it could be done for SIMD. So they might be sending it straight in there and just making sure. The 64 might just be because because there's a lot of padding here. So this guy, yeah, it could be because they're just sending it straight to SIMD and or the GPU. So we take this. So I think the next one, I have to respond to my blick. We have 4 times. Okay, so what's 181? Ah, so yeah, okay, I was making the wrong assumption there. So we are now done with count 0. And as I rightly deduce, that value they read here is it's not used for anything in the file. Again, like I said, I'm not saying it's not used. I'm just saying for our purposes here, we're purely interested in anything that might be used for the file. That's why I'm skipping these functions, because I know for a fact there's no file pointer being passed in here, so this can't manipulate the file. So likely just initializing a structure. The same with this. We did have to look at this because obviously this does it does initialize just purely to see how this 16 byte thing is initialized. So we're now down here. So what's A1 do? So if I come back to my file pointer, what's A1? A1 is the first pointer in this, and that reads 8 bytes. So if we come back to our file, let me start off here. So that's 8 bytes. Holy moly. That's actually 7,000 values. Let's try this. If we go, what did this say it was? So we read this into 181. And then we go, what was it? 7896 times 4 bytes. 31 kilobytes. And that should give us this. I feel like we're missing something though. I feel like we should be going longer with this data. That 4 times in the sense of, oh, it is. Alright. Here. What you do? You see, I think I'm missing something. 104. What is 104? Or is it, hold on, back here? No, that still doesn't make sense. So, alright, 96. So A1 plus, so what's initializing plus 8? Is A2. What's going on here? So this is, so we know for a fact, okay, so we get 8 bytes from the file. And I'm 90% certain that this is where we want to be, because because obviously this buffer we get here, pretty sure this is where we want to be. But then what's, I'm guessing maybe it's passing in, wait, no, wrong place, up here. Oh, here we go. This I think is the memory file of eTable, which I guess the game has so much type information. So 0, 8, 16, 24, 32, 40. Ah, yeah, so we're just reading the buffer again from the file. Oh, too complex. Yeah, so plus 96 is the buffer. Yeah, that makes sense. And then 104 is the actual count. Yes, that makes sense. Yeah, so we're not missing anything. It doesn't make sense. So if we take this guy again, then maybe I'm just, yeah, 4. Okay, so let's assume that that's correct, because it can't be anything else. So the read 8 bytes. That brings us all the way down here. Actually, yeah, you know what? Yeah, no, I was looking at this wrong. Yes, that does make sense. So now we're here at this data, because this data looks completely different. You can kind of see how like the data changes. So we've got what looks like, you know, these arbitrary values, and then now we have what looks like a table of numbers. So obviously this is a table as well, but this one looks a bit more different, as in the values are a bit different. You can kind of see how things change if you look at this versus this. So yes, that's correct. I'm just being dumb. I think it's because Grim is here. So we can do unc. Just get that off. Unc count 0 is equal to unpack read. And then we just read that times that. Oh, sorry. We want. I will read 2 i's. Doesn't matter. Yeah, fucking Q. Fine. Fine, I'll make it at 64-bit. So yeah, so now we've deduced that. Where's my cursor gone to me? Yeah. So now we have 4 times, and then 4 times UC, and another 4 times UC. That's like 4 times UC, and this one is 8 times UC aligned to 16 and shifted 6. I'll just throw that in some brackets. Oh no, sorry, that's 16. 64. What am I doing? You can just erase this. Not like it's a pen. 64. So we then lead on to a value. So if we just throw this down here, so we're moving on to just an unc 0, which is 4 bytes, and then we just read 4 times UC 0. Excuse the handwriting, it's quite hard to type writing that thing when it's all the way over there. So yeah, so now we can move on to this. Now we're looking at header 4. So now at this data here, and right, so and again, I'm making the assumption these values are 1 for now because there is only. If we come back up here, so header 4. So this is our header 4, and just to confirm actually that my names are correct, yeah. So sorry, header 8 is it? Come on, what have I done here? Oh, so this one was header 8, but we already know it's 1 for now, so we can make the assumption as 1. We don't need to read. It doesn't look like it's actually doing it. Hold on, so they passed it in as A2. I mean, yeah, it is doing stuff. Where are they getting this from? So 52, so it must be assigned that somewhere. There 8 signed on. Yeah, I'm guessing it must assign it here somewhere. Yeah, that's what they're doing. So this will loop. So for however many values is in this, so if there's like 2 or 3, it'll do this. So technically, what we should be doing here is, I mean, we can do it because actually doesn't really cost a whole lot. 4i in range of, what was it? It was header buffer. Actually, we can go H0, H4, H8, and H12, just so they kind of match what I have in IDA. And we can do 4i in range of H8. Even though, like I said, it's always been 1 in every file I've looked at, we can't make that assumption because it might eventually end up. Well, for this test, it kind of doesn't matter, but I will do it because it I leave this one the same though, or this way for now, because this requires a bit more code, because they actually do, first off they parse all the bone counts and then they do some other stuff if it's higher than 1. I'm gonna leave that the way it is for now. Yeah, so 4, it is 1 for now, so we're alright, but next one is 4i in range of H4. And now for H4, what we're gonna do is, so we come back down here. So we're gonna start off by reading kind of similar to the previous ones. So we come to Where does this end up? Oh. Again, I'm gonna have to close that file and reopen it. It's HXD. Like a piece of crap, we'll just hold. If you do that, HXD will lock the file. Kind of fucking annoys me. Open up this first. So, oh wait. Wait, no, wrong one. Where is it? Oh, right, yeah, no, hold on. Yeah, this is where I want to be. I accidentally did it from the start. Oh my god, it's that guy. It's that guy. Oh no. Oh no. Oh no. Alright, so we have this. I mean, the reason this kind of probably looks the same as the other ones. This could be like this could be indices, and it just so happens to start off with this high value. But this starts off by reading this value. So we now go. Okay, so we're now at. Create a little subsection here. So we're now at this point where it's like. Let me open it actually. Read across here. So we're now at this section where it's essentially what it's doing is we come down here. So it's essentially going, all right, so we're starting off with this is H4. And we're going, all right, first off, we're reading an unknown value, 4 bytes. That function, the next function doesn't look to be doing anything. It then checks if it's greater than 0, that's fine, I don't care about that. And then we are doing 4 times unk. But then we're reading another unk, 1 unk. And we're essentially doing the same thing. 4 times unk 1. And this particular section just seems to be doing this all the way down. So we can see recount, then actually read the data, recount, read the data, recount. Actually, what the fuck does this do? So okay, so this one just looks to read the data count as is. So we now have. Sometimes I have to see my cursor here. Got unk 2, 4, and then we just read unk 2. Right. So if we take that initial little, this part I don't care about. This is purely probably, like I said, the internal game structure is probably 32 bytes each. So, and not 100% sure what they're doing here. Like what, same with byte? Yeah, I don't really know. What's 640 do? Ever get initialized? Again, that could have to do with the whole, like I was saying earlier, with oh well, but I know the data is there, so let's make the assumption it's there. This I was about to say that this might have to do with the fact that the game has the version stuff, but then it doesn't look like it's what it's doing. Yeah, sorry, so let's move on to this. We're in range of H4, and we're saying that for each element here, we're going to do unk. And just to save some time, I'll read this here. Let me just do f.read 4 times unk. And we are going to do the same. One I'm interested in, I might stop it before it gets to the last part because I want to see what actually was that. Oh, yeah, what's going on here? Why is this now failing? Marv, you absolute waste of time. You join the chat and the code fails. Let me remove this because, yeah, I don't care about that. Go back to oh, hold on. Don't tell me it's like. Yeah, why the hell is this failing all of a sudden? Why is bone count 1? Or is it because I did something here? Oh, is it not like these? Oh. Melvin, what did you do? I don't know, do I have to wrap it or something? No. What the fuck? Alright, let's just go back to this being header. What the fuck? Why is that now failing? What the fuck? I love when code breaks like this for absolutely no reason at all. What are they doing? What are the dog doing? Marv, I swear to God. Size 15, yeah, it looks fine. Oh. Oh, I love Python's indentation. That's the only thing I was language. Right, there we go. Get that out of there. Get that out of there. Kick the ball. Alright. So. Oh my god. That's one of the only things I hate about working in Python is you end up with weird shit like that where you accidentally leave an indentation somewhere and it's like completely broke the whole program. Actually, what the hell is going? Oh, oops. How did I get reverted to it? I thought I made that 8. Oh well. Marvin, I'm blaming you because you joined the chat. Oh yeah, okay. So we're looking like yeah, yeah. All right. We're looking like we might be getting somewhere with this. So if we go unc2, and then unc2 is literally just reading bytes. Or actually, I need to confirm that. So if I come back up to this guy, plus yeah, okay. So it's purely just reading. This is 4 times, and then it reads this one, and then it just, or maybe hold on. 32. This one's doing something a bit different. So alright. Marv. Sorry, we love you. So we have these two are like together. So it's for a header count. So we then have this situation here where we're reading another integer. But the integer they read makes no sense because it's like a float. So maybe I'm off somewhere, but then I don't think so because oh yeah, because it's 0. So yes, this function won't run because yeah. So we will go unc 2, and then we will go if unc2 greater than 0, Then we will read, I don't know, another unk. 672, 664, 72. What are they doing with 656? I guess they're doing nothing. So we will essentially read another 4 bytes, which I think looking at this does nothing. And then we will read this. But that's only if this value here is greater than 0, which it is not. So we will skip that. And we will now move on to this. What are we doing here? I mean, oh, okay, so we are actually very close to the mesh data. So we're making some good progress here, in the sense that we are now getting very close to the mesh data. So this is the mesh table of where to store all the meshes, and of course, these will have different LODs. So the pack metadata will tell it where to go for the LODs. So, but we are now getting very close to the mesh data. So we're on the right track here. And purely as a test, let's try and throw another file in here. A completely separate file. I don't know, but the potato fade out sounds like a cute. No, that one looks fecked. Never mind. Let's try a different one. Let's sort by size. Maybe we have Alex Casey suit. Alright, so let's try this one. I think some of those files are a bit screwed. I don't think my export is working quickly. So that's why some of them are not, they don't look correct. Or otherwise there is data in it that's completely different. So if we pop him in there, this ends up here. And if we pop him in here, yeah, okay, maybe it doesn't look. I mean, it kind of looks like we're at the right place, but maybe I'm missing something. I mean, I haven't actually. We're still. Yeah, I mean, the mesh data is down here. We should be here. That's where we are in the other. Or am I printing if held correctly? Yeah. Let's try and print this where we are up here. Does this look correct? It looks like we got lost somewhere. Definitely got lost somewhere. Does this file? No, this file does not have. We got lost somewhere up here. This one starts off here. Oh yeah. Okay, so for something went wrong here during the. Or no, I'm not in the right file. So yeah, so we're here. Yeah, something went wrong here. Or oh no, sorry. Yeah, no, okay, no, it's correct. Because we are. We starting here. So what about here? Are we correct here? 91999. And it looks correct. How about we drop this guy down here? Yeah, we're definitely misaligned. Maybe here. Because if we look at where we start off here, so we're if we consider here to be where we're finished here, so something's wrong here. Because that looks correct. So we are getting through to this part of the file. But for some reason then we're failing, or we're what'd you put it? We're screwing up somewhere after this, where possibly we're not parsing some data, because I mean the other file got would look to the correct location, but this file isn't. So, or maybe I'm just missing some stuff. That could also be it, but it doesn't look like it because, I mean, yeah, hold on. So we start off here. Now this is this part here. What was it? Yeah, it was this one 8 times. So if we even just skip this, because I'm 99% sure that's okay. So if we come to this guy, hit F5. That brings us here. That's, and now we're here. 42. We're becoming misaligned somewhere. That looks okay. How about this? So he finishes up there. Again, that kind of looks correct. We're kind of starting what looks like new data. And then so this one ends up around here. Right, yeah, so so we have this. Yeah, so this file actually has data within here, which the other one didn't, so we're obviously messing up somewhere here. Let's go back to IDA. And let's go back down here. So it starts off here, so we know these two are correct. We're getting to the right location in terms of these two, which is equivalent to these 4 times 4 times. So what we want is something's happening here. Let's hit. So Chunk 2 is 540. Yep, it is 540. Read 4 bytes, which actually I don't know what I returned. According to this, we just read the values, but something tells me we need to do something different. Unless I was about to say, unless the initializer thing in here does something. So byte count. Something tells me we need to do 4 times this. Because this all look like ints. Let's just try and make that something. I know that's not what the game's doing, but that could be because I'm making the wrong assumption about what that thing does. 4 times 540, 2160. Copy that. That looks a bit more correct, maybe? I don't know. I just don't think it should be, hold on, 540. That's just correct. So if we do 540, that brings us to here. Then it could be correct. Yes. Something that's saying like 4 each. There's only 1 entry in this table, so it's not like we're forgetting, it's not like because we're not parsing each entry. So it's obviously where we're failing. So it's not a whole lot to digest. So we start off by reading the 32-bit int. Check if it's greater than 0. So we're reading this value here. In this file, it was obviously 0, so we were skipping this. But now this one actually has some data in this section. So 373. Not sure what that's doing. 373. Okay. So 540. Then we read another integer, which is that one that says 373. Doesn't look like it's doing anything with that right here, at least straight off the bat. But yeah, I mean, it's just 672, which, yeah, I mean, it's doing what these other functions are doing, which is just initializing this structure. And then it's reading 672, but it is just reading bytes. So it's just reading 540 bytes. Is there anything else I'm missing? O2 label, that just sends it straight down here. And again, maybe I just need to continue on with this. Maybe this is correct. I guess it doesn't look like it needs to look correct. But then, what do I know? I make the game. So we end up down here. Maybe it is. And then this just looks like this is just a continue. It kind of looks like. I mean, I'm kind of, the reason I'm saying 4 times looks more correct is because we end up hitting this. We do it by 4 times. We end up hitting this negative value, which kind of looks like where we're supposed to end up because, again, going by the whole patterns, this looks like the odd one out. If I was to try and include this in the table, This would actually be logically where we should end up. So for now, I must be missing something within these functions, maybe that are like maybe doing, expanding that into 4 times. But I don't think so, because this is just doing. This is just literally assigning it. Not doing anything special. V4. Yeah, it doesn't look like it's doing anything special. So, alright, let's continue on here. I'll skip this for now. We'll go back to the other file at 0, because I know any issues we're having are related to. Put that guy back in there. And that should now bring us back to that with this file here. So, where I want it. So, we've now read this. We're now here. And that brings us to reading this value. Here. So A8. Back to that file table. What's the offset of A8? X38, which is like what, 50? I don't know. I mean, it's like 56, is it? 30 is. Yeah, I think that's 56. I need to confirm that. Yeah, 56. So 0, 8, 24, 32, 40, 48, 56, I think. 4 bytes. Make a whole lot of sense. I mean, we're hitting this data now, which kind of looks like where it's supposed to be. So I think what I need to do for this other file to see what's happening to the data here is maybe just debug the game and see what it's doing. For this particular one, this looks like these are like 1.0. I mean, this one doesn't, but it looks like we're reading like 12 bytes here for float. A1, A2, A3, A4, A5. That makes sense. We're up a debugger. See what it's doing here. I will need to find this function in the game's memory though, because this game uses ASLR, which is pretty common for modern apps anyway. I think it's like a default. It'd be pretty funny if my original breakpoints are there. But I don't trust them because they might be for other stuff I was working on. Let's just delete all these. Oh no, I don't want to run. Oh god, I have to back out of it. I want to hit the loader function. So we're getting to this point, and I think I might set a breakpoint actually here because we're getting to here. back out some of these. We're getting to here, and then we're kind of failing. So let's get the bytes for this. We're calling, yeah, that looks like it. Copy this whole row of bytes. That'll probably bring us to where we want to be. 22. Down. I need you for now. Let's look at where this is in memory. Pretty funny if the game's bloody exe file updates. It's already updated. Exit the main menu. You know, it'll probably be easier if I come down. We're talking about here, maybe. Yeah, that looks about where we want to be. I think. Come on. All plus 48. Yeah, that's about it. Alright, let's hit continue. And we'll immediately hit a breakpoint because the game has already started to load some stuff. So obviously I can't tell what this is, but we hit, is it, oh jeez Christ, I don't even know. Is it trace into F7, step into? Yeah, there we go, F7. Yeah. See that? Yeah, we're going to this, which is likely going to call file. So this might tell us where, yeah, this might tell us where the data in memory is for this particular. Yeah, here we go. So it's going to move these into the particular registers for this particular one, and then we can use that then to do so. R8, I think, is it? Oh wait, no, this is mem move, so that the function layout is a little different. And mem copy, mem move. Ah, do you know, we can wing it. It's only true. There's only 3 parameters to this function, isn't there? We can just wing it. We can go moves 1 is RCX. Is RCX where you want to be? Owned up. Nope. Alright, maybe. No, that's the number of bytes, maybe. Maybe RDX. Oh yeah, RDX looks more like it. Alright, so let's copy address. Go to this address. And yeah, so this looks about like what we were looking at. Only this actually has data. I don't know what model this is, but it looks simple, which is good. I'm happy with that because we can probably use this as an example. Oh crap. Forgot to press shift. Copy this out of memory and just try parsing this. Yeah, I don't care about the mesh data for now, or at least the actual raw mesh data. Testing. Yeah, let's just throw this in here as mesh.binfbx so I can just completely overwrite this file if I need to. I don't want to overwrite some of the stuff we've exported, even though I can just export it again. So if we follow along to what they're doing, we can do mesh.binfbx. I can hit F5. We've already failed. Fuck. Why are we failing? I mean, actually, yeah, what the fuck? Oh, alright, so this actually has multiple bone tables. Wow. Alright, finally found one. So yeah, so maybe not a good one to use as a test, because I don't want to deal with one that has, but at least this is an example of one that actually has, so you can see what's different. Yeah, so they do actually have, you just parse these 3 and you probably have to go through that 3 times. That's actually interesting. So I don't even know what this is. I mean, I just see bow and piece. This is probably just an arbitrary prop in the game that's just animated. Because like I said, they do have that GDC presentation on what you call it. What was that? Mesh, vegetation through skinning. So they probably use skinning all over the place for anything really. So let's get out here. Let's see if we can try and hit one that is 7. Jump to here. Was it RDX, wasn't it? Oh, window. Yes, this one has stuff as well. Or I might just need to wing it and just say, look, we have to implement the multiple bone tables if I want to make this viable to work with or to test. Yeah, this one is 5. Jesus, where have these been? Oh, my testing. Where have they been? Is there a way for me to see how many entries? Did they store it in a register? Maybe that I can quickly look at, because I just want to find one that doesn't have multiple tables, so that we can kind of, or like I said, maybe I just need to bite the bullet. You know what? Let's bite the bullet. I love biting bullets. Let's just I mean, it shouldn't be that hard. So we'll do bone counts. We'll do 4i in range. What was the header? Come back to this guy. Bone table count header 12, which is 0, 1, 3. Header 3. And we'll just need to parse those. So bone counts. It's weird that they're doing this for the bone counts at the start, but then the other ones are just like, yeah, we'll just go through all of that. Yeah, it's weird that they kind of like do this pre-loop to grab all the bone counts, but then in the other ones it just, yeah, there isn't none of that. So we'll do bone counts, dot append. Not too really concerned about performance here in terms of, you know, pre-allocating the bone count array or something like that. Struct unpack dot read 4 up in 0. We don't want a whole lot. And then now we can do, get rid of that, and then we can do 4 bone count in bone counts, and then there. Oh yeah, okay, so that's done that correctly. They're not all the same, interestingly. So yeah, the first table has, so this leads into my speculation that maybe this is it's commonly used for stuff like, you know, props, where unless the character is right on top of a prop, they don't care if it's, you know, high quality. Very common for games like drop animation frames and drops bones when, you know, when it comes to computing animation frames when they're at a lower LOD. So we now need to do the same thing for this, because for this one we're going to do again the same thing. I'm going to do 4. This is header 8, so 4i in range 2. So header 1, or is it 2? It's header 2. Sorry. Everything up until this. Then should leave us here. Syntax error. Oh fuck. Yeah, 5. Yeah, so like this graph kind of shows how they talk about um GPU based skinning for vegetation. So like they're kind of using this all over the place. Um and they'll probably say like, the trees that are, 50 miles away, we only want 12 bones for them, but the stuff that's up close, we want to really make those details, so let's have them have like 100 bones. So that's likely what they're doing. Bone transfer, yeah. Pretty cool to see. It's pretty cool. I always find it interesting to see this. They do use mesh shaders very heavily. So if you're aware of what those are, very, very, very mesh shader driven engine. Made it quite hard because it made it quite hard when we were first trying to use RenderDoc on the game. RenderDoc, actually, I don't think it wouldn't work for me. I had to get Thomas Cat to use what's the name of that one that Nvidia have? Is it Insight? I think that's the name of it. Yeah, that he was able to get that to work, but RenderDoc wouldn't. But even if we did get RenderDoc working, both Insight and RenderDoc do not support mesh shaders properly, like as in looking at the data that's being sent to it. So all we could do is just look at the shaders. That's why I have the shader, which is a lot in its own right, but I'd like to see the actual data being sent in and out of the GPU. So we are now down here. We're still debugging. So pop a little f.tel there, a little cheeky f.tel, little cheeky f.tel. Let's pop that in there. So we are now at 16 to 40, which, holy crap, that's way too far ahead where we want to be. Although technically this shouldn't be possible, actually. So let's come to this guy. We shouldn't be this far ahead, should we? Good. Yeah, I didn't copy a whole lot. All right, let's instead use this one because I'm after, like, since I skimmed that file. Oh my god, go away. Oh, that starts there, but really the file actually starts all the way up here. Again, to start the file. ED4. Maybe. Okay, so this file starts here. Let's make sure we actually get all the file. Okay. Yeah, it looks like we're getting all the file. Oh my god, I did it again. Press control. Screw this program. I have to find the file to start again. Marv, I blame you. He's still here. There's a lot ahead of that in here. Did I just go past the... Try and find a simpler one. So back to our debugger. Copy value. And yeah, this looks simpler. You can actually see that this is definitely where the file ends. Alright, so just capture all of this. Yeah, let's just go maybe. Oh, okay, so maybe that won't work. 5 megabytes. I know, just accept it. I don't know. Don't scream at me. That's not that's undefined. Go away. 512 kilobytes. Just want to make sure we're getting everything. That'll do. Yeah, that'll do. Right, so this one is saying is when it hits that it's there. So I'm not sure remind myself, where were we actually breakpointing? Yeah, so it's this guy here. Bula bula. So we finish up here. All these breakpoints. Yeah, we're failing here for some reason. Are we correctly getting to this location though, at least? Is in the bone table we're parsing that correctly. So we get to here. Yeah, it looks correct. Maybe we want to print out each one to see where it's actually failing. So we get to here. I have to tell if that is correct or not. It kind of looks. I mean, it kind of looks correct. I don't know. The next one ends up 43. Yeah, okay, that's definitely not correct. So something's going wrong there. Yeah, some. Yeah, so we need to figure out why it's doing that. So one of these is obviously not doing too well. So we start off really good. I mean, is it this? I mean, I'm gonna say no because they're all 5. So even if we got one of them wrong, they're all 5. So we would succeed anyway based on the fact that they're all 5. Let's maybe do bong bong bong. Can I tell the file pointer from here? I wish it was like C#, where you can actually see because the position is stored as a property, and you can actually see it in the debugger. You can actually see what the current file position is, but I don't think we can do that here, can we? Special variables maybe. Oh, there's just special. Yeah, there's just Python variables. So it doesn't. I don't think it lets us see this. Maybe. Ah, you know what? It's gonna be just easier to put that in here. See where each one of these ends, and where to begin. So let's start here. At that. So again, that looks correct. We start off by reading this, which is 5, and this. So this guy, that one looks correct. Where we get to 23,488. Again, that looks correct, yeah. So we're here. We read 4 bytes. Again, this looks like This looks kind of like a bone indices. So I'm wondering too. That's what I was saying. I was wondering if this is like a parent index table. So maybe, yeah. So I'm wondering if these, if the problem was if I look at if I look at this literally and say, where was that count? It was up here, wasn't it? That one that was like 5e. Yeah, this one. 94. None of these have 94 entries. And some of them, like, I know this one's pretty close, but I've seen some examples, like the other model where, like, they were, like this one, where it's like 700 entries in that index table. So I'm wondering, what is it even used for? So we look at this, look at, that one's correct. It looks correct anyway. F, but I was pressed the wrong button. This one finishes up around here. Yep, that looks good. Finishing up where we want to. Looks fine. Again, another 4-byte read, or well, 4-byte entries that are 4 bytes each. And then we finish up around here, and then we've got another 4 to read, and I'm guessing maybe it's this one is wrong. We end up around here, and then we're now here. So actually, no, it looks like we're correct because we end up now in this, which. Nope. Hold on a sec. Gramian, I'm gonna kill you. You and your mobile phone emojis. Oh my god, it's Marv again. Alright, so this does not. Yeah, okay, so we're something's going wrong here because we're good up until here, but this now doesn't look correct. This looks like. So maybe. Oh yeah, no, this needs to be part of this. Yeah, okay, so that makes sense. There we go. And then it's 4 times this. Yes, this is So now if we use this and we go pipe. Oh yeah, there we go. So now we're in business. So let's get to down here. And again, the game seems to do something where it like checks. So if I look at this, it seems like if the header table 8 value is greater than 0, That's where I'm wondering if this comparing to 652. So I'm wondering if they're connected, like, because obviously it only executes the logic related to that header value that's at 4 if 8 has a value. So I don't know, but we check. Yeah, if 8 has a value, then come in here now 4, but we're checking 4 against this. So where did they initialize that? They could initialize it in here, to be fair. Yeah, very likely. Very likely it's in here. Is it like passing in 24? But there's a lot of bytes in here. 112, yeah, definitely. So it might be like comparing it to the value that's at 8, and if it's less than or greater than, then don't continue, or something like that. I don't know. But let's assume that's its own independent value for now. For I in range header 4, which is 1. And this is where we start parsing out these guys. Oh, yeah, get rid of this guy. So in theory, these two. So hold on. If I put that in there, the game is so we're now at the same mesh file that the game is loading. I should end up, once I hit that, here. So once I get to here, so if I hit this, and no, we are way off. Way off. So if I pop a little cheeky printf.tell, so basically when the game gets to this point, the pointer is here. So we're a bit off. Slight bit. So let's see where we're going wrong. So we finish up with these around here. Oh, wrong. Right. So when we get to this point, we have that. So 92. I make a safe assumption that this is good, because if this was, it would fail like you saw there. If this is bad, like we'd try to read stuff that's way too big, or we'd get misaligned very quickly and then would be completely way off. Let's have a look at this. 312. Alpha. Am I missing something in here. Store in the stack. Let's try and see if we can read it. RSP. Was it RSP plus 598? It's just 5. Yeah, so we're okay. So this is executing this code, because I thought maybe something here was maybe skipping. But they're correctly executing this code. Read that. Blick blick. Right. So gonna raise that. Value then gets assigned in here. Same thing. That's it. That's So can't see what's going wrong here. So read the 4 bytes there. Do this again. So yeah, okay. Alright, I see where I'm going wrong. Take this out. Put this out here. This is not part of the loop. Fuck. Right. So now we should get to the right location where we want to be. Go up print tell there so I can tell where we are. These all look correct. Yeah, okay, so that makes sense. Just simple case of take this breakpoint out. Now we should end up. Yeah, exactly where we want to be. Alright, perfect. Which is oh crap. Moved wrong location again. Which is exactly where the game is. Which is right here. So at that exact location. That's pretty much where we want to be. So now we can start throwing some more in here. I say it's like sometimes it's just easier. Just debug the game. Simple mistake of me looking at the decompiler wrong. So if you look very closely, this loop, I wrongly assumed all of it is part of one loop. Sometimes with Ida's indentation and all these jumps and stuff, it's hard to see. You can actually see this part is outside the loop, so it does this independently of the count. So that's why sometimes it's easier. Just can help with debugging human error like that, just to literally just look at the debugger and see what the game is actually doing. It does help too because I'm able to follow along with the game now to an extent. So now while I'm here, I'll keep the game open because now I can actually follow along and see what I'm doing. So this, so now we should end up at, hold on. So we should now end up here. We do all that. I'll hit F5. Print after oops. And now we should end up here. So if we continue debugging this, where do we want to get to next? I think there's a jump in here, so it's going to jump exactly where we want to go next. So if I go, I think it's going to call this 48, and it's going to call 28, which is this one, which is 40. So then it's going to come down here and call, is this the one it's going to call next? Yeah, so it's going to call this one next. Again, a good opportunity to see where exactly we are. So if I do that. This is, as I assumed, reading 4 bytes. So where exactly are we? For DX. DX follow and dump. Yeah, so we're right here. So I'm going to rename this to read float. I'm going to assume it's reading float. So my goal here today is to get to the mesh stuff. So if we can get that done. So left.read4, I will just comment that as floating point number. So I'm going to assume a lot of this stuff we might actually need. A lot of it we can probably skip because I'm going to assume a lot of this is like stuff the game uses for its own internal physics and stuff like that. But like I said, I did see what looked like parent indices in there. So that probably is where they're stored. And then there's a way the game maps all that together with the own table we had from the start of the file. But that is something I need to look into. Or it might just be nothing. So let's see what this is doing. Is this doing 140? Okay, so it's going to read 130. This is going to go. We're going to go for 4i in range of unk. And we're just going to read a floating point number. We're doing indentation is right now. Just throw in. Oh crap, my indentation is wrong again. And let's see where that ends up. 48. So if we go here, this is just going to keep. Maybe not. EX 4. Alright, here we go. Alright, so it's going to keep doing this, reading 4 bytes at a time. It's done. And then it's going to read another float. It's going to read a lot of floats actually. So let's actually count these. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 floats. Interesting. So 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually doesn't sound right. Maybe I'm counting that wrong because it's weird that they read it. 1. There's 3 bundled together. There's 6 straight away. 9, 10, 11. Yeah, okay, no, there's 11. Can throw the f.tel at the bottom of the file so that we know exactly where we are. We end up here. And then again, 4 I in range of header 1. What we're going to do is read floats. 1, 2, 4. 4 floats. And again, I'm not sure what it's doing here. Probably some more stuff we'll have to get done here. A minute to play, but let's see where this ends up. Could just be one of the values from the header, to be fair. So this one is going for and that's where we're ending up. So let's see where the debugger takes us. So I can just kind of skim past a lot of these. When do we hit this? 278. Yep. Down there. That's R15. So R15 plus that, then 278. I'm guessing that's one of the values from the header. We'll figure out which afterwards. For now, I'll just do. I suppose I could copy out this. I don't have any search in here. Yeah, I don't think I is not very good at that. What was it plus? Where did that start doing? So here, plus 632. What does that get initialized to? Again, it's probably initialized somewhere else in one of those functions where they like, this is probably, so plus 632 is probably like an internal data struct. And then they just pass that into another function. They just do plus A, plus 9, blah, 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 blah. So it's probably like a struct that gets initialized in another function within here that gets called. But for now, since they're all 5 again, I'm just going to make their very wrong assumption to just call like, we'll just do plus. Come back up actually to where this is. So, well, it's saying if we have any values. So let's just do if header 1 brace of classes Python does not equal 0. Again, never seen a case where it's not. It's always something, but then we've I wrongly made the assumption I've never seen files that had multiple tables, but now we have. So 2, 3, 4, 6, 7, 8, 9, 10. Okay. So 1, 2, 3, 4, 5, 6, 10. And that ends up here. And that makes sense because we are likely getting we are very close, if not at the mesh data, because this is the mesh data. So we've now successfully traversed all of this initial data. So you can see how we've slowly built up a bit of an understanding of not what the data is, but what dictates the size of the data. So we can now see we start off with some initializers, then it's 48, 4, 4, 4, 8, and then padded. The same for this. We can see this needs to be, so these are linked, so technically this function only runs if this has data. Again, they always seem to have data, but we can't make that assumption. Again, this one, where was it? This one runs only if there's data, reads some random value. So we are now getting very close to the mesh data, I reckon, because I think it's in one of these functions even. Because I remember having to look at it, because I remember just skimming through all this straight to where I thought the mesh stuff was being read. And it might even be down here. Yeah, you see the way, so IDA has already identified what it thinks is a DirectX device, and you can see how straight away they're probably loading this data directly in. I haven't labeled that as PP device. I might have actually, but maybe. I've seen IDA actually identify a DirectX device by looking, because this isn't obfuscated, so it's probably able to see from another function that the game is initializing a Direct3D device, and it's able to see that is the DirectX device. But maybe that might have been, I might have labeled that, I'm not 100% sure. I don't think I did though, because I think I overwrote my original exe file. But I have seen IDA identify like DirectX and stuff itself, because it's common stuff. So one of these is the mesh loader, which God forbid which one it actually is. I remember it being like yeah, maybe it's in here. Can't be this one, because so we get past all this. Not that one. It's not that. Could be this one. Nope. Maybe this. Nope. Maybe this. Nope. This will be an interesting one to look at, because yeah, here we go. So yeah, so this is where the mesh data actually is. So you can see here how first off we start off. I think these are like 4 bytes. So again, this is accessing the. I don't know, is it accessing? Yeah, it's accessing the memory file directly, which I must label for ease of use. You can see here how there is some stuff in here that is variable length. So not every. So where traditionally you might look at this and say, oh, it's just a table of meshes. Let's go down to that where that is. You might just look at it and say, oh, so it's just a table of meshes. But the problem is this the size of each of these entries is going to change not only in every file, but even within this file, because some of these won't have skinning data, so they might. Because what I identified as well is if we look at, is it this guy? This loads in the attributes within this, which I think are here. I think, or it might be it might be these ones. So there's like 8 or something, or 5 attributes. And it loads them in, and then I think it maps it to, I don't know, I can't remember, is this list the size of each data type, so destroyed, or I can't remember, is this a DXGI mapping table? I think it's the size of each entry based off of the value, what data type it is. So it's a quick way for the game to know, oh yeah, I just do 4 times vertex count, or I do 12 times vertex count. I think that's the only variable. Oh yeah, you also have this, where it's like, there's more different data that's in here. So there's a lot of stuff in here that's variable length. That's where it gets complicated, because if you're just looking at this from the perspective of the file, it can be quite hard to actually decipher what is what data within. Like, you look at this, you it can be quite hard to see what in here is actually variable. Like, what changes, and like, obviously we're not worried about what changes. We're worried about what changes that dictates the size of the data. That's the big thing with my initial step with trying to figure out the file format is I'm more interested in, first off, doing this, getting this initial high level view of the file, where I can start going, now, okay, I know this, and this dictates this, and this. So I actually have the mesh stuff kind of figured out, I think, if I look in here. Yeah, so we start off with reading a bunch of integers. These do not dictate. I think some of these are the vertex counts and face counts. These have no use. Then we have MIBOI. MIBOI is the attributes. So we read, again, like I think some of these, like attribute count, attribute type, offset within the buffer, which buffer we're using. Because if we go up to the mesh data, we have like vertex bytes, and we have position only vertex bytes. And I think there's a flag there that dictates 1 or 0, dictates whether we're in here or whether we're in here. And again, this data was the stuff I was mentioning before, where if we look at, this guy here, we scroll down here to the, you can see, so this stuff is completely separate to the mesh file. So like some of these in here might be, and what these then correlate to is, I think if I look at my DMs with, hold on, scroll up, and here, my god. I remember sending it. I always thought I remember sending it to Luke. God, where is it? I remember like figuring out how to map those. Okay, here's a good screenshot I have of the mesh one. So, you can kind of see how, because I can't be arsed going to find that in the file. You can see how, first off, with the pack metadata, it's a very simple thing. If I come back here, this guy. So it just looks, first off, the magic number, that's always constant, that PKMD. Then we have for each. For each entry, actually, hold on. Where is it gonna be? Oh, it's looking right at the screenshot. So, so we have a count. Oh yeah, no, okay, that makes sense. So the number of entries within here, this 0 correlates with, there's a table in the pack file of all the classes that are used. So that will then correlate, the game will use that to look up the class in game of what to use. And basically then this is just the starting offset and the end offset. And then, so if we take one of these, are probably the mesh data, we then pass it in here, and then this will just traverse some, what's it called, metadata about the file, so that the game can have immediately handy. So, but yeah, if we go back to the mesh, the whole thing of deciphering this method to try and figure it out is so that I can very quickly just say, yeah, we have lung cancer in here as well. Trust me, my variable names, you will love them. I remember there was a project I made for HydraX, the one that would parse the what was it called? The text sets for the material, because I need to build a table of all the properties. And I called it like poop sock or something, and I can't find it to this day. Something like that, and I can't find it. It's probably on this PC somewhere, but it's just, I just throw down random stuff. It's when you're naming things is one of the hardest things in computer science, I think someone said. But you can see here we can actually get a very high overview. So yeah, we're for each mesh, start reading a bunch of stuff. Okay, we've hit something now that actually dictates. So this is very blinked. Done. Then we're here. Having a clue what this does actually. Still haven't figured it out. But I know it's used. So I think we made good progress. We've gotten basically a file, a script in Python. Doesn't get us all the way there. We're still a bit away from actually getting to the mesh data, but I think it's a good progress of a high level parser for the initial part of the file if it has bones. So this will actually get us all the way down here very quickly. So we can actually try this on another file. So let's try to find MPC. Again, yeah, that's not correct. That one's I think that one was exporting correctly, where the tool is not correctly exporting some stuff. Yeah, again, this has some stuff. Actually, you know what? I'll just copy all this in here. And then run that. Yeah, so we're actually now... Yeah, this looks like we're getting down to the mesh data. So, we're getting somewhere in regards to being able to, at the very least, if we just wanted mesh data and bone, and if all we cared about was getting these bones, don't care about anything else, just these bones out, and if all we cared about is getting them out and getting the mesh data out, we're getting very close to the point that we can just skip this entire section of the file, and then get straight on to the mesh data. So we'll probably leave it at that for today. I think this should be a VOD, but I'll make sure it's like uploaded so that it can be referenced later if you want to go back and view anything. Maybe next week I might try and keep these to the Saturdays. I'll of course I might tip away at Alan Wake throughout the week. That's just the way I work, but I might try and keep Alan Wake to the streams. Oh well, if hey, thanks. Any patrons, much appreciated. There should be a VOD after I'm done, so if you just popped in and it's over, you can probably just view the video. We'll probably try and keep Alan Wake. I know Texture Hawk got the slightly better vote, 1 extra vote, but I don't think Texture Hawk would have been a very interesting thing to make a video on. The Alan Wake stuff is just more, we can do a lot more with it on stream, especially in Texture Hawk's current state. It's just more boilerplate. But we made good progress here where we're able to get to the mesh data, or well, we're close to it, where we can start to get down to here where we're parsing the mesh metadata. And then maybe next week, yeah, so I'll try and keep Alan Wake to the streams. We can try and get the mesh data out next week, maybe try and get an actual, like an actual mesh. Because at the moment, the stuff I showed off is purely hack. It's just me telling the tool where to go. So if we can try and get a script going that it can take any file and poop out a literal Warzone mobile. I'm not looking at that anymore. I've handed that over to Desto, so I'm not looking at that. I don't know what he's going to do with it, but he did seem interested and seems to have been implementing it into Cordyceps so that it can work just like the other tools, but I'm not really working on that. I was probably interested in the arm emulation, so I probably won't look at it any further. But the stuff for Alan Wake, yeah, we'll look at it next week again, try and get a script going for the kind of get out the mesh data. So yeah, thanks for tuning in. Marv, you suck.